Wildfires have the potential to destroy hundreds of thousands of acres of land. Traditional wildfire monitoring methods often rely on satellite imagery. When you need updated data at a specific location, the satellite needs to pass overhead at the right place and the right time. And they can also be obscured by clouds and smoke, which can introduce delays in detection. That's where our solution comes in. A distributed sensor network that uses ground-level data such as humidity, temperature, and vegetation growth to predict the risk of wildfires even before they start. This allows homeowners and firefighting agencies to be better prepared and take precautionary measures early on, ultimately saving lives, property, and nature.
So here you can see our sensor node, which transmits data to the base station over LoRa. Since it's assigned to be placed in a remote setting, there are no Wi-Fi capabilities. Instead, its sensor readings are communicated back to the central database. So now we have our sensor node taken apart. Right now it's all encapsulated in this 3D printed case that we made. Right here we have the ESP32, which is connected to a battery. And this ESP32 is connected to a bunch of sensors, like the light sensor over here, the LoRa sensor, and within this case is a soil sensor hidden in this tube over here, a temperature, humidity, and pressure sensor hidden under the case. Lastly, we have an antenna poking out of the case to transmit data wirelessly to the central database. And we have this hole over here to get the light sensor data, and it's strategically placed within this hole so that it gets the light sensors from the readings to read vegetation growth.
So here you can see our base station, which is a Raspberry Pi Pico W connected to a LoRa module. The LoRa module operates at 900 megahertz, and here you can see the LoRa antenna. Upon receiving data from the node, which is placed out in the field, up to 2 miles away, the data that comes into the Raspberry Pi is presented here, and it sends in real time to a Postgres SQL cloud-hosted database, which is hosted on Supabase. Okay, so this is our dashboard that shows real-time changes to fire risk computations over time, and also the raw sensor reading values. So we have temperature over time, humidity over time, pressure, light, soil temperature, and soil moisture, all of which these show the last 15 readings as they update every 3 seconds. And you can see that the fire risk computation is very low. Currently, it sits at 12.3, and the FRP estimate is also very, very low, since, as Jerry is showing in the top right corner, the device is just placed in front of the URIS library patch of grass.
Our first test is going to be light intensity. So as light levels go up, we can see the sensor readings go up. And this corresponds to lower vegetation density, so we can see the fire risk go down over time. We tested the device with a heater, and as temperature increased, the fire risk also went up. Our third test was performed using a humidifier, and as relative humidity went up, the fire risk went down. Lastly, when we added water to the pot, the higher soil moisture resulted in lower fire risk. The machine learning model uses MODIS fire detections from the United States in 2024, which was filtered based on locations in California. We sampled environmental data from Google Earth Engine at 24 hours before the time of the fires and created matching non-fire samples. Our model learned from these samples and predicts the fire risk and projected intensity.